All right, so in these last examples, we're going to be putting permutations, combinations, and arrangements using factorials and factorials with repeats kind of all together. And the tough part about these problems is knowing when do I do what? When is it a permutation? When is it a combination? So hopefully these practice problems break it down and kind of help you understand. Again, remember, if we're going to use permutations when order matters. So, in combinations, order doesn't matter. So let's just try to keep that in the back of the mind as we go through this. So it says, a farmer has 10 different trees, each a different species. How many ways can each of these be planted? So one thing to think about, when you do something like the permutation function, or the combination function, you have a set and then you're picking a smaller set, right? So with this one, we just have one number. We know we have 10 different trees, right? They're all different species, so there are no repeats. So the number of different arrangements here is going to be 10 factorial. Let's compute that. 10. Remember, to get to our factorial, we go to math, and we arrow over to that probability. And we go to number 4, which is our factorial. Hit enter. So there are 3,628,800. Different combinations, okay? This one says a farmer has 10 trees, 5 maple, 3 oak, and 2 buckeyes. How many ways? So 5 maple, 3 oaks, and 2 buckeyes. How many different ways can these be planted in a row? So again, order matters here, because if I switch them, if I go to this order, that's different than the one I have over here. But this time I have repeats, right? So even though I have 10 trees, I need to divide the repeats out. So remember, with factorials with repeats, you need to open a parentheses if you have a multiple in the denominator. How many m's are there? 1, 2, 3, 4, 5 m's. How many o's are there? There are 3 o's. And then, times 3 o's times how many b's are there? There are 2 b's. So we're going to do 10 factorial divided by 5 factorial times 3 factorial times 2 factorial. So 10 factorial divided by parentheses 5 factorial times 3 factorial times 2 factorial. Close our parentheses. So there are 2,520 different ways we can plant these types of trees. 2,520. Double check that. Yep, okay. All right, the next one. It says there are 7 people were in a race. How many different ways can we present awards for first, second, and third place? So this is n. We know n is 7 because we have 7 people in our race. So that's going to be our first number. Now we need to decide, does order matter or doesn't it? I think in this situation, if I am the first place person, order matters to me, right? Because I came in first. So since I have first, second, and third, we know that order matters. Because again, if I switch second and first place and say, hey, it doesn't matter who finished the second and first, somebody's not going to be happy. So this is a situation where we're going to do permutation. And then how many awards are we giving? We're giving 3 awards, 1 for first, 1 for second, 1 for third. So for permutation, remember, we put the n in first, so we put the 7 in first. Then we go to our probability function, and we select permutation. And we are permutating them in groups of 3, first, second, third. And it looks like there are 210 ways. This says find the probability of selecting 5 winning numbers from 1 through 27. In this case, it's not super clear whether order matters or doesn't. I've talked to some people about lotteries, but with lottery, order does not matter. So in this case, would this be a permutation or a combination? It's going to be a combination here because the order doesn't matter. How many different combinations are there? Well, there are 27 numbers to choose from, and I'm putting them in combinations of 5. Oops. So this is going to be 27C5, 27, go to our probability menu, select C, and then put in the number 5. 27C5 is 80730. So there are 80730. It looks like there are 80,730 different combinations. But go back to the problem. It says find the probability of selecting the 5 winning numbers. So it's asking for a probability, right? This means it needs to be written as a fraction, decimal, or percent. So how many winning combinations are there? There's only one winning combination out of 80,730 different combinations of those numbers. So that would be the probability of winning. The next one says when testing for current in cable with 7 color-coded wires, the wires need to be checked in pairs. How many different tests are required to check every possible pairing of 2 wires? In this case, I want you to take a second and let's think about whether order matters or it doesn't. If we think about it a little bit, hit pause, think about it, but if we think about it, what we're saying is, if I've got a blue wire over here and I've got a green wire over here and I check them, is that the same thing as checking the green wire with the blue wire? Are these the same thing? And I think they are, right? That's still checking the green wire and the blue wire together, right? So this means that BG is the same thing as GB. This means that order does not matter. So since order does not matter, we're going to use a combination, and we have 7 wires that we are testing, and we are testing them in pairs, so groups of 2. So 7 C2 gives us 21 different combinations of those wires. All right, the last one. Let's take a look at these. It says there are 12 members on the board of directors for a large company. So here we know N is equal to 12. If they must choose a chairperson and a secretary, how many slates are possible? Think about it. For electing roles, chairperson and secretary, would order matter or does it not matter in this situation? I think in this case, order would matter, because if I say Joe is the chairperson and Steve is the secretary, then I switch it around, say Steve's the secretary and Joe's the chairperson, that's a different arrangement, right? So this is going to be, here order matters. So this is a permutation, and I have 12 people to choose from, and I am assigning 2 roles. So this is 12P2. So 12, math, go to permutation, and we are permutating groups of 2, so there are 132 different ways we can select a chairperson and a secretary. All right, the last one says if they must form an ethics subcommittee of 4 members, how many different members of the subcommittee are possible? Let's think about a subcommittee. Would order matter with a subcommittee? Well, in this case, I don't think order matters because, again, there's no roles being assigned. So since there are no roles, order does not matter. So how many different people do I have to choose from? 12. And I'm putting them in combinations of how many people? We are putting them in a subgroup of 4. So this is 12C4. 12. Go to our combination, which is number 3, and we pick 4. So there are 495 different subgroups possible.